All right, folks, so here we'll continue with the 6.2 note. We'll actually go a little bit out of order. I wish I could, and actually I might rearrange these for the handout for the next class I teach this to, but we'll go through example 4 before going through example 3 here. Now, where we're looking, we're going to follow the same kind of strategy that we were using last time. But here we're going to play around with it a little bit more. We'll explicitly work here with some of these angles. Now, excuse me. Now, when we work here, there's a little bit of an extra step. So here we have the tangent of 5 pi over 4. So our first step, we know we're going to sketch that angle. Okay, so 5 pi over 4, I'm looking at something like this. I know 4 pi over 4 is is halfway around my circle. So 5 pi over 4 is going to be something like this. There we go. We've sketched our angle. Nice work, guys. Now we need to find our related acute angle. So when we're working with our related acute angle, bear with me as I try to get the same colors as we used last time. We'll use orange for our related acute angle. Fantastic. So if I have 5 pi over 4, sorry, I'll just label that in here, 5 pi over 4, then my related acute angle, if I'm working here in quadrant 3, then I know my related acute angle lies somewhere like this. So that means my related acute angle is going to be half of one circle, and that's pi radians, plus my related acute angle will equal 5 pi over 4. So maybe we'll state that right in here. So 5 pi over 4 is going to be equal to my related acute angle plus pi radians. Fantastic. My related acute angle plus pi radians. And then I can rearrange this here. Okay, so that means I'm working with 5 pi over 4 is equal to, 4 pi over 4. Pi over 4 plus alpha. I can rearrange. I'm working with alpha is equal to 5 pi over 4 minus 4 pi over 4. That is pi over 4. So my related acute angle in this case is pi over 4. So now I'm going to check, and we have a bit of a procedure over here. We want to check to see if our ratio is going to be positive, if our trig ratio, and that here is the tangent of 5 pi over 4, if we're expecting that to be positive. So we'll check that along with our cast rule, and our cast rule says, okay, CAST. In this quadrant with my terminal arm, my tangent ratios are going to be positive. And if my tangent ratios are positive here, that means the tangent ratios in this quadrant would be equal to the tangent ratio in quadrant 1 with the same related acute angle. So that is my tangent ratio of my related acute angle. In this case, I'm working with pi over 4. Okay, good job us. Now we know how to evaluate the tangent of pi over 4. Oops, sorry folks. We know how to evaluate the tangent of pi over 4. We jump in with our special triangle. All right, so we come up with our special triangle. We should be masters of sketching this now. Side length 1 in here. According to my Pythagorean theorem, that means this third side length is the square root of 2. All right, both of these angles are pi over 4. I'll label that one. We'll use it. The tangent of pi over 4 is going to be my adjacent side over my opposite side over my adjacent side. And if I'm working with my opposite side over my adjacent side, I'm working here with 1 over 1. So that means the tangent of 5 pi over 4, sorry, as I rearrange this here, I'm hoping it's not too distracting as I speak. The tangent of 5 pi over 4, that's what we're solving here, is equal to the tangent of pi over 4. And the tangent of pi over 4 is equal to 1 over 1. That reduces just to 1. All right, so we're going through the logic in a slightly different order here, and I'm hoping that it resonates with you. First, we check to see if our ratio was positive or negative. And then we stated right in here, we restated our tangent ratio in terms of the related acute angle. We were able to do that. It stayed positive in this case because we were working with tangent in the third quadrant. Let's try now the next one, the secant of 5 pi over 6. All right, well, we'll try that out. First, we need to make sure we sketch 5 pi over 6. All right, we know how to sketch something like that. That's a little bit less than pi, so we're working here. 5 pi over 6, my angle should look 5 pi over 6, my angle looks something like that. All right, now I need to come up with my related acute angle. In this case, because I'm working in quadrant 2, my related acute angle plus 5 pi over 6, that's going to be equal to my related acute angle plus 5 pi over 6 is going to be equal to pi this time. Okay, that's great. If I use that logic, I should be able to rearrange for alpha. So alpha is equal to pi minus 5 pi over 6. I'm working with my related acute angle of pi over 6. All right, good job. Now I need to check, okay, secant. Now my secant, that's going to be 1 over, you know what, I'll work on a slightly different color there. There we go. That's going to be 1 over the cosine of 5 pi over 6. All right, so 1 divided by the cosine of 5 pi over 6, it means I'm working with a cosine ratio here. So let's put our cast rule into play, C-A-S-T, and then I need to check, okay, is cosine going to be positive in quadrant 2? No, it won't be, because sine is my only primary trig ratio that's positive in quadrant 2. So since cosine is negative, and bear with me while I give myself a tiny bit more space right here. There we go. I'll shift that down. I think that'll work a little bit nicer. Since cosine is negative here, then I can rewrite this ratio in terms of my related acute angle. But if I'm doing that, I need to respect the idea that my ratio will be negative. So I'm working here with 1 over negative the cosine of pi over 6, where now I'm working in terms of my related acute angle, not 5 pi over 6, just pi over 6. All right, from here, now all I need to do is evaluate the cosine of the cosine of pi over 6. We should be able to evaluate that by using, you guessed it, our special triangles. So nice and easy, we're sketching our special triangle. We have a side length 1 down here, a side length 2 up here. Whoops, a side length 2 is our hypotenuse, and we have the square root of 3 over here. All right, we have pi over 3. That was an original angle of our equilateral triangle. And then we have pi over 6 up here. And it's that pi over 6 that's going to be where we're focusing. So we're evaluating. Okay, so the cosine of pi over 6 is going to be equal to my adjacent side over my hypotenuse. And if that's the case, the adjacent side is the square root of 3 divided by my hypotenuse, that's 2. So if the cosine of pi over 6 is equal to root 3 over 2, then 1 over negative the cosine of pi over 6, bear with me here, and I'm just going to, I really didn't plan out my spacing here, I apologize. That is going to be equal to 1 over negative root 3 over 2. And that's equal to negative 2 over root 3. All right, well done. So this is how we evaluate whether we're using a reciprocal angle or a reciprocal ratio or a primary ratio. We follow these same steps. All right, so you should be able to handle here C and D. D is actually missing a pi symbol right there. I will include C and D in the note that I upload to the classroom, but we won't go over those in the video right here. If you have questions about how we go through those, if you compare your work with the filled in note on the classroom, then feel free to send me an email. Then we'll jump up, and I'm hoping that strategy can walk us through up here where we're evaluating these trig ratios, because we can follow the same pattern, right? So we're working here, and I have the sine of 4 pi over 3. All right, the sine of 4 pi over 3, let's start off with a nice sketch. 4 pi over 3, that is something like this. I know it's more than pi, and it's less than 3 pi over 2. Good, and then I need to make sure I find my related acute angle. Now, my related acute angle should be on this side. It's to the closest x-axis. And in this case, I can see, okay, so pi is over here. So I know pi plus my related acute angle is going to be equal to this 4 pi over 3 that I started with. So 4 pi over 3 is going to be equal to pi plus my related acute angle. A little bit of calculation here shows me I'm working with pi over 3 as my related acute angle. Fantastic. If I'm working with pi over 3 as my related acute angle, I need to sketch my special triangle. Now you'll notice we're sketching a number of special triangles. We're sketching them over and over and over again. When you're working through on an assessment, sketching these special triangles is a part of your solution every single question. So it's not enough to just sketch your special triangles at the top of your page and then refer to them throughout a summative. No. You need to make sure they're a part of every single solution. Might it be helpful to sketch them at the top of your page for you to look at as you go through? Sure, but you need to make sure they are sketched again. You need to make sure they are included whenever you're relying on them to evaluate an angle. So we're working here, all right, I have a right angle here, side length 2, side length 1, side length the square root of 3. And I would have pi over 3 in this angle here, pi over 6 up top. Nice and easy. Okay, so I'm evaluating the sine of 4 pi over 3. Hang on, 4 pi over 3 isn't in there. Right. Pi over 3 is. So I'm evaluating pi over 3. But in order to do that, and I apologize, I'm going in a slightly different order on this one, and that's okay. We're following all the same steps. I'm going through a slightly different order. I need to connect what I'm doing over here to my initial problem. So the sine of 4 pi over 3, in order to do that, I need to use my cast rule. The sine of 4 pi over 3, I'm working here. Okay. According to my cast rule in quadrant 3, which is where my terminal arm is, tangent ratio is positive. That means my sine ratio is negative. If my sine ratio is negative, that means that the sine of 4 pi over 3 is going to be equal to negative the sine of my related acute angle. That is negative the sine of pi over 3. Now it all makes sense. Now we can interpret this. I'm looking for the sine of pi over 3. Let's try that out here. The sine of pi over 3 is equal to my opposite side over my hypotenuse. Pi over 3 opposite to that is the square root of 3. My hypotenuse is 2. Good. So then I substitute this in way up here. So the sine of 4 pi over 3 is equal to negative the sine of pi over 3, and that is, it's equal to negative the square root of 3 over 2. Fantastic. So let's go about example 3b. We'll go about this using the same order in which we solved example 4. I think that may have been a little bit more straightforward for us. So the cosine of 5 pi over 6. We always start with a sketch. 5 pi over 6. Okay, I know that's slightly less than pi, so I'm working with something like this. And I have 5 pi over 6. All right, good job, us. Now we need to find the related acute angle. And I'm sure you're noticing some repetitiveness in here. That's a good thing. If you're recognizing it as repetitive, by all means, try pausing the video here, solving the problem on your own, and then unpausing it and comparing your work with mine. We see our related acute angle here. It is the angle between our negative x-axis, in this case, and our terminal arm. And in this case, I can see that 5 pi over 6 plus my related acute angle, that will make the full half circle. That will make pi. So angle pi is equal to my related acute angle plus 5 pi over 6. I can rearrange. I'm working with my related acute angle is going to be equal to pi over 6. Good, so if my related acute angle is pi over 6, and I can combine that logic with my cast rule right here, C-A-S-T, I know I'm working here in quadrant 3. And if I'm working here in quadrant 2, if I'm working here in quadrant 2, my sine ratio is positive. If sine is positive, cosine is negative. So if my cosine ratio is negative here, then this is going to be equal to negative the cosine ratio of my related acute angle, pi over 6. We know how to evaluate the cosine of pi over 6. How do we do that? Using our special triangles. So we're sketching it once more. We're practicing it every single time. We should be getting a little bit faster at sketching in our special triangles. We should be getting a little bit more comfortable with the logic involved in sketching these special triangles. I cannot emphasize it enough. It is going to be worth your time to practice the logic of these special triangles rather than just focusing on memorizing how it works. Memorizing how it works will not improve your skills. All right. So I'm evaluating the cosine of pi over 6. The cosine of pi over 6 is going to be the adjacent over the hypotenuse of that angle. The adjacent side to pi over 6, that's the square root of 3. It's divided by 2, the hypotenuse, square root of 3 divided by 2. You're noticing some common themes in here. These same numbers are going to keep showing up again and again and again. Okay, so if the cosine of pi over 6 is root 3 over 2, that means negative the cosine of pi over 6 is negative the square root of 3 over 2, and that's also equal to the cosine of 5 pi over 6. So, well done, folks. You should be able to handle C and D on your own. Like I said before, I will include those in the solutions that I post on the classroom. I do just want to go over, I believe there's one more, you know what, there are 2 more example types that we'll go through. All right, so here we're going to go through the same kind of logic we just did, but in a backwards direction, because in this case, we're told what the ratio is equivalent to. We're told the value of the ratio. We just need to find what angle brings us the value of this ratio. And they give us a little bit of a restriction here. We're going to be working with our angle in between pi and 2 pi. Okay, so if it's in between pi and 2 pi, that means I'm either working in this quadrant or in that quadrant. Fantastic. So, excuse me, let's try this out. Sorry, folks, I'm not feeling my best, and I'm having some coughing fits at times in here. Okay, so we know we're working for the square root of 3 divided by 2. So then I need to ask myself, okay, what kind of a special triangle has the square root of 3 as one side and 2 as another side? Because I know I find this ratio from using a special triangle. That's a special triangle we've just sketched about 4 times already in this video. We can sketch it one more time right here. Okay, side length 1, my hypotenuse is side length 2. My Pythagorean theorem says my third side is side length 3. I have pi over 6 up here because it was the original pi over 3 angle divided by 2. It was cut in half. And then I have pi over 3 down here, obviously a right angle there. So then I ask myself, okay, if I'm working with a cosine ratio is equal to an adjacent side over a hypotenuse. Fantastic. Well, an adjacent side over a hypotenuse, that's equal to the square root of 3 over 2. Then I need to ask myself, which angle has an adjacent side of the square root of 3? Well, the square root of 3 is right here. That is adjacent to what angle? Pi over 6. So it's that pi over 6 that we're going to use, and then we'll play around with it a little bit more. We need to be a little bit ready. So I'm working here, and I say, okay, well, that's great. I'm working here with the square root of 3 over 2, but it's not necessarily the square root of 2. Sorry, it's not negative the square root of 2 that I'm working with down here, because my related acute angle is pi over 6. So this is going to be equal to negative the cosine of pi over 6, right? I need to keep that negative. That's the key. That's what I was talking about. So if we're keeping that negative in place, then I need to ask myself, okay, in which quadrant will I be working? Whoops, did I lose an arrow down there? There we go. So I'm working down here. I know if I'm working in quadrant 4, then my related acute angle is somewhere like this. If I'm working in quadrant 3, my related acute angle would be somewhere like this. Now, this ratio that I'm working with is a negative value, and it's a cosine ratio. So that means, can it be in quadrant 3? Absolutely, because in quadrant 3, my cosine ratio is negative. Could it be in quadrant 4? No, it could not. Cosine is my only positive ratio in this quadrant, so I'm not allowed to be working in here because in this particular case, I have a negative sign in front of my ratio. This is a negative value. All right, so if that's the case, now I can see where I'm going. Now I can see what I'm doing. So where I'm working right here, I know that my related acute angle, which is given up here, we found it, it's pi over 6. We know we're working in quadrant 3, and we can use that logic to come up with the value of theta. So the value of theta here, we know if we're in quadrant 3, then theta is going to be equal to pi, which is halfway around my circle, plus my related acute angle. All right, now I know the value of my related acute angle. That is pi plus pi over 6. All right, since I know that value, pi plus pi over 6, I'm working with 7 pi over 6. That's my value for theta. That is my final answer. Great work, folks. I'll encourage you to try out, let me see right here. Try out working with the cosine of theta over here. Now, actually, we'll play around with that a little bit. I'll simplify that for you. The square root of 2 over 2 is equal to 1 over the square root of 2. All right, so we're using that first step. We should be able to use that step to simplify to find our value for theta. And if you're not overwhelmed yet, great job. If you are overwhelmed, maybe pause the video, go through some practice problems, go through a little bit, take a break, stand up, walk around, open a window, grab some fresh air. But if you're still moving quickly, if your brain is still working well with us, then we'll work with example 6. Example 6, okay, so we have a point, -3, 4. It lies on the terminal arm of an angle theta, and it's in standard position. So if we're working here, then first of all, we might notice, okay, this is not, they're asking us to sketch it. This is not a unit circle, right? Because if our point -3, 4, let's sketch that point. Okay, -3, x is -3, y is 4. My point is here. That means my terminal arm lies there, and my angle can be measured something like this. All right, now that might seem pretty straightforward for you, but I suspect some of you would have felt a little uncomfortable coming up with that sketch on your own, and that's okay. That's why we're practicing it. All right, now we need to find the value of r. What is r? R is our radius, right? And so if I'm finding the value of my radius, I can use my Pythagorean theorem for that. I know this side length is 3 units. I know this side length is 4 units because of the coordinates of this point. So if that's the case, and really maybe I'll sketch my terminal arm a little bit more carefully. My terminal arm should only go to that point. It should not continue beyond. So my radius then is going to be equal to the square root of 3 squared plus 4 squared. All right, nice and easy. I'm working here with the square root of 9 plus 16. I'm working with the square root of 25. I'm working with plus or minus, or really I know I'm working with 5 because the radius that I'm working with certainly needs to be positive. All right. Now we should be able to come up with primary trigonometric ratios for this angle theta by using the side lengths of this triangle. Is this a special triangle? No, it's not. But that's okay. We have all of the side lengths. And you might say, well, hang on, Mr. Pasotka, there's no triangle there. And maybe there's not yet, but we can sketch one in, right? We can place our triangle right on that x-axis. There's a right angle right here. Our side length here is 3. Our side length there is 4. And really, it's a side length that reaches towards -3, but side lengths themselves, they can only be positive. So we're working here, and we're going to say, okay, we're working in quadrant 2. What do we know about our trigonometric ratios in quadrant 2? Oh, well, we know, according to our CAST rule, C-A-S-T, we know our sine ratio will be positive, and our tangent and cosine ratios will be negative. So we'll work in here, and we'll work, I don't know, we'll use green to evaluate our trig ratios. All right, so our sine ratio is positive. And if our sine ratio is positive, we're working with the sine of theta is going to be equal to my opposite side over my hypotenuse. All right, my opposite side to this angle. Okay, so now we need to be a little bit careful, a little bit unsure of ourselves. We're working in here. This would be my angle alpha. So my opposite side to the angle alpha, that's 4. My hypotenuse is 5. Now, our radiuses, our radii, when we're working, they will always be positive, okay? So whenever you are calculating a radius, it's always going to have a positive value. Good job, us. All right, now our cosine ratio, we're expecting this to be negative. So let's take a look. Our cosine ratio, we're working with the adjacent side over the hypotenuse. Okay, well, my adjacent side, you'll notice here, my adjacent side is -3, right? It reaches -3 units in. You could either combine your cast rule with a positive length here, or if that confuses you, stick with your negative. Keep that negative in place. So -3 divided by the hypotenuse divided by 5. That is our ratio. Notice we're leaving these as fractions. We could put them into decimals in these particular cases because they do simplify nice and straightforward. But for the most part, we're working in grade 12. We should be working with fractions. We're creating good habits if we're doing so. All right, so our tangent ratio we're working here, we have our opposite side over our adjacent side. Okay, so the opposite side from angle alpha, I'm working with 4. My adjacent side to angle alpha, -3. I should, because I'm in grade 12, put negatives in the numerator. I'm working here with -4/3. Fantastic. Now, what we need to do is we need to work here and we need to come up with a radian value theta. We can use a calculator if needed. And the key here, the key is just recalling the skills you learned from trigonometry in grade 9. You worked on it in grade 9, you worked on it in grade 10, whoops, you worked on it in grade 11, and here we are in grade 12, and it's probably been a long time since you've done this. Let's take a look at this first ratio. Okay, so if the sine of theta, working with question D, the sine of theta is equal to 4/5, that means I can use my inverse sine function. Remember doing that? Of course you do. So if you're using your inverse sine function, what that does, now that you have a bit of an understanding of inverses, what that does is it takes your sine function and it undoes that. So we're taking the inverse sine of the left-hand side. We're taking the inverse sine of the right-hand side. They cancel out on the left. I'm working here with theta is equal to the inverse sine of 4/5. You'll need to make sure your calculator is working in radians at this point. Is it going to come up with a ratio in terms of pi? No, it's not, and that's okay. So we'll put that into our calculators. The inverse sine of 4/5, and we're working here 0.927 radians. There we are. That's how we go through a problem like this. Some of the questions in the textbook use this exact skill. They're set up in the same way. So try this out. At this point, you should be able to handle all of the practice problems from section 6.2. Nice work, folks. If you're struggling with any of the questions, feel free to send me an email.